Welcome to video lecture on well hydraulics in groundwater engineering. This recovery. Suppose a well is pumped at a constant rate Q, the pumping is stopped after a time T1 and it is desired to compute the residual drawdown S dash after a time T dash since pumping stopped. The recovery of piezometric head can be determined by considering a negative discharge, that is the recharge, for the time T dash. For a small value of R and the large value of T dash, Jacob's approximation can be made and the residual drawdown S dash after the time t equal to t1 plus t dash, since pumping started, can be obtained from the equation. S dash equal to 2.303 q by 4 pi t log 2.25 t into t by r square s minus 2.303 q by 4 pi t log 10 2.25 t dash by r square s. Or otherwise S dash equal to 2.303 q by 4 pi t log base 10 t by t dash. In this recovery method, the residual drawdown in a pumped well or a nearby observation well are measured at different time intervals after pumping is stopped. For a semi-log plot of S dash versus T by T dash, the transmissibility T can be obtained, similar to Jacob's method, as T equal to 2.303 Q by 4 pi into del S dash, where del S dash is the drawdown difference per log cycle of T by T dash. So the graph shown here is the drawdown and recovery of groundwater level in the vicinity of pumping well. So the first portion will gives you the pumping and the next is the non-pumping period. When the pumping started, there will be a decrease in the water level in the well, and when the pumping stopped, there will be increase in the water level in the well, which is called as the recovery. The storage coefficient S can be determined from the value of drawdown at the time the pumping was stopped. S can also be determined from the time drawdown plot of the data during pumping also. The drawdown resulting from variable pumping rates can be determined by the superposition technique as S equal to Q1 by 4 pi T W of R square S by 4 T into T1 plus T2 plus Q2 minus Q1 by 4 pi T W of R square S by 4 T into T2. The value of W of U for corresponding values of U can be obtained from the table. Baylor method. Skybitsky has developed a method for determining the coefficient of transmissibility from the recovery of water well in a well that has been bailed. For large values of t, S dash equal to V by 4 pi t into t, where V is the volume of water removed during one Baylor cycle and t length of time since Baylor was removed. If the residual drawdown is observed at some time after completion of n Baylor cycles, removing the same quantity of water in each Baylor cycle, then S dash equal to V by 4 pi into T 1 by T1 plus 1 by T2 up to 1 by Tn. The Baylor method is thus applied to a single observation of residual drawdown after that time since bailing was stopped becomes large. Slug method. So this is very similar to Baylor method. A quantity of water V or slug is injected and the residual heads S at times of injection is completed or noted. An arithmetic plot of residual heads versus reciprocals of times of observation produces a straight line whose slope approximately substituted in the equation S dash equal to V by 4 pi t into t permits computation of coefficient of transmissibility. This method has serious limitations since the duration of the test is very short and its use is restricted to an artificial aquifers of small to moderate transmissibility. Image well theory. When a well is located close to a barrier or rechargeable boundary, marked deviations from a radial flow system occur. Solutions in such a case are readily obtainable by the application of the method of images. An image, which may be an imaginary discharging or recharging well, creates a hydraulic system which is equivalent to the effects of a known physical boundary on the flow system. In essence, Images enable an aquifer of finite extent to be transformed to one of infinite extent. This enables the radial flow equation to be applied to this modified system. A common field problem is that of identifying and locating aquifer boundaries. Pumping test data can provide quantitative answer after application of the method of images and non-equilibrium equation. If a pumping well and an observation well are located near an unknown impermeable aquifer boundary, an image pumping well will furnish the equivalent hydraulic flow system. So the image shows here the time drawdown graph by the location of barrier and recharge boundary. So the pump test data will be noted down with respect to observation S and then time, and there will be a deviation in the curve is obtained by the influence of the barrier boundary. So from the laws of times, we have r square by Tp equal to r1 square by T1, where r is the distance of the observation from the real well, r1 the distance of observation well from the image well, Tp is time since pumping began to any selected drawdown before the boundary affects the drawdown, T1 time since pumping began where the divergence of the drawdown curve from the type curve equals the selected drawdown of the value of R1 obtained may be taken as the distance of impermeable aquifer boundary from the discharging well. Alternatively, if the time t0 for zero drawdown is selected from the Jacob's time drawdown curve and is the time at which a change of slope is indicated, the distance of aquifer boundary from the discharging well is obtained from the equation r square by t naught equal to r1 square by t, which is same as the earlier equation. The distance r1 obtained from both equations gives an arc on which the image well lies. Data from two or more observation wells are required to locate the image well from the intersection of the three arcs as shown in the figure. The aquifer boundary is midway and perpendicular to the line joining the pumped well and the image well. Partially penetration of wells. Many artesian wells do not penetrate through the full thickness of the aquifer, and many wells are provided with strainers with only a portion of the thickness of the aquifer. In such a case, there is a vertical convergence of streamlines near the well, resulting increased entrance velocity with increased drawdown. Cozzini developed a formula for the capacity of well partially penetrating an artesian aquifer. Qp equal to Q into alpha 1 plus 7 root of Tw by 2 alpha b cos pi alpha by 2, where Qp discharge in partially penetrating well, Q is the discharge in artesian well. For complete penetration, alpha is the penetration, and then the fraction L by b, where L is the length of the strainer and b is the thickness of the aquifer, and Rw is the radius of the well. The radius of influence in calculating Q is assumed to be about 3000 meter for artesian well. Qp in unconfined aquifer is obtained from the above equation by replacing B by H. The radius of influence in calculating Q in a water table aquifer may be assumed as 300 meter. The discharge ratio Qp by Q for the same drawdown as a function of penetration fraction and well slimness L by 2 or W is also shown in the figure. So the figure shows the partial penetration of well where the well is penetrating partially into the confined aquifer for a length L. And this is the well so which is in the unconfined aquifer. Van Helsing Lee evolved a simple empirical formula for the ratio of drawdown and discharge in a partially penetrating well based on the data obtained from a series of tests very similar to an electric analogy method. SWP by SW equal to 1 plus log V by RW by log R by RW 1 by alpha power 0.75 minus 1. Similarly, QP by Q equal to 1 by 1 plus log V by RW by log R by RW 1 plus alpha power 0.75 minus 1, which is applicable for alpha is greater than 0.1. So the graph shows the discharge ratio Qp by Q versus penetration with respect to the well slimness. The equation obtained for the discharge ratio by various investigators may also be expressed in terms of non-dimensional parameters. For Shimai, Qp by Q equal to phi of alpha, Decli Qp by Q equal to phi of alpha R by Rw, comma L by Rw R by B, Muscat Q by Q equal to Q phi of alpha R by Rw, comma B by Rw, comma B by Rw. Cosine Qp by Q equal to phi of alpha, comma B by Rw, when assume Lee Qp by Q equal to phi of alpha, comma R by Rw, comma B by Rw. In its most general form, the discharge ratio can be expressed as Qp by Q equal to phi of alpha R by Rw, comma B by Rw, comma L by Rw, B by R, B by R. Well losses. The ultimate drawdown in a well measured at a designated rate of Q from the continuous pumping for a given period is different from the theoretical drawdown due to well losses. The total drawdown is made up of head loss resulting from laminar flow in the formation, head loss resulting from the turbulent flow in the zone close to the well face, head loss through the well screen, head loss in the well casing, and SW equal to BQ plus CQ square, SW by Q equal to B plus CQ, where B is the coefficient for formation loss due to the 1, and C is the quotient of well losses due to 2, 3 and 4, and as dimensions of T square by L power 5, SW by Q equal to specific drawdown, and BQ is the formation loss and CQ square is the well loss. A plot of SW by Q versus Q gives you a straight line. The figure whose slope gives the well loss coefficient C and intercept on the SW by Q axis gives the formation loss coefficient. So the image shown here is the graph between the specific drawdown SW by Q and the discharge, and then the slope gives you the well loss. The Roraba has modified this graphical method when the drawdown is given by SW equal to BQ plus CQ power n. The value of n varies from 2. Collector well. A collector well is a horizontal radial well used to extract water from an aquifer with induced infiltration from the surface water like river or lake. For decades, collector well has been the system of choice for developing large quantities of water very efficiently and economically. As an alternative to conventional vertical walls or surface water intakes, it is replaced by a collector well. The collector well consists of a central concrete shaft or caisson equipped with horizontal screens radiating out in a water-bearing sediments. Water is drawn into the central caisson through these horizontal screens or laterals where it collects and it is pumped to the ground surface. Collector wells are particularly well suited for developing unconsolidated aquifers where recharge can be induced from a surface water source. So the image shows is a collector well. Infiltration gallery. An infiltration gallery is a horizontal drain made from open, jointed or perforated pipes, or a block chain drain which is laid below water table and collects the groundwater. The infiltration gallery needs soils that are permeable to allow sufficient water to be collected. The gallery should be surrounded with a gravel pack to improve the flow towards it and to infiltrate any large particles that might clog the perforations. The image shown here is an infiltration gallery which is provided below the ground level to collect the water on the surface. The galleries are often used in conjunction with the other water supply system as a means of increasing the quantity of water intake in areas of poor water yield. In this instance, one or more galleries are built which drain into a central point such as a hand dug or a well or a spring box. These are called as collector wells. When an infiltrant gallery is built, it is important to protect it from contamination by locating it uphill and at a minimum safe distance from the latrines. The distance is site specific, although a figure of 30 meters has been suggested as a general guideline. The gallery should also be constructed to ensure that unfiltered surface water cannot enter. So thank you for watching this video.